Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? This question was first posed by meteorologist Edward Lorenz in a 1972 presentation. The idea quickly captured the public's imagination, permeating the culture through movies, songs, books, and even memes. The idea, dubbed the butterfly effect, explores the fascinating concept that minor actions can lead to huge, unintended consequences. Why does this concept resonate so deeply with people? It touches on a primal question. Can we predict the future? In this video, we will understand the scientific basis of the butterfly effect and try to answer this question. If you appreciate the content, please show your support by liking, subscribing to the channel, leaving a comment, and sharing this video with your circle. Your engagement greatly aids the algorithm. This video is inspired by the book Chaos, Making a New Science by the American journalist James Gleick. Starting from the accidental discovery of meteorologist Edward Lorenz, who was trying to create a model of long-term weather forecasting, Gleick successively reconstructs the whole chain of sudden insights and unusual experiments that led scientists to the realization that there are universal laws of nature that were still unknown to them. Gleick not only tells the story of the birth of a new science, but also reflects on the ways in which scientific progress occurs and the role of mad geniuses searching for unconventional solutions in spite of existing knowledge. At the close of the 17th century, Isaac Newton revolutionized our understanding of the physical world with his groundbreaking principles of motion and gravity. These discoveries seem to offer the secret to predicting almost everything in the cosmos. In 1814 came Pierre-Simon Laplace, a prominent figure in French scientific circles. Laplace proposed a fascinating mental experiment that is still controversial among scientists and philosophers today. Laplace envisioned an omniscient entity, later dubbed Laplace's demon, capable of knowing the exact location and momentum of every particle in the universe at any given time. Armed with full knowledge of all physical laws, this hypothetical being could foresee the future trajectory of each particle and tell its history. The question arises, is such a demon even theoretically conceivable? Given the scientific advances of that era, the answer seems to lean toward the affirmative. Scientists of that time believed that it was possible to predict the motion of all celestial bodies, the exact time of eclipses, and even the appearance of comets for centuries ahead. If this mind is broad enough to comprehend all this, the future, as well as the past, will appear as the present in his eyes, Laplace wrote. This is absolute determinism, the notion that the future is predetermined and we are only waiting for it to come. Later on, however, Laplace's demon was severely criticized. After the development of quantum mechanics and the discovery of Heisenberg's uncertainty principle, it became clear that quantum systems are beyond the control of the demon. They are fundamentally unpredictable. Even Newton realized that some systems don't lend themselves to classical mechanics, especially the three-body problem. The three-body problem is to predict the motions of three planets, given their mutual gravitational attraction. That is why it's called a problem. Stephen Strogatz. The three-body problem, a notorious enigma in the world of astrophysics, has puzzled scientists for several centuries. At its core, this problem studies the complex, unpredictable interactions that occur when three celestial bodies, for example, planets or stars, are subjected to mutual attraction. The complexity arises because, unlike simpler two-body scenarios, the motion of three interacting bodies quickly devolves into chaos, making long-term predictions nearly impossible. Imagine the Earth and the Moon calmly orbiting the Sun. This duo behaves in a fairly predictable manner, thanks to a relatively simple gravitational interaction. Each month, the Moon completes its orbit around the Earth without any major surprises. However, at a rogue planet, like the scenario depicted in Lars von Trier's apocalyptic drama, Melancholia and the future trajectories of these celestial bodies become a puzzle. Isaac Newton himself tried to solve this problem by developing his groundbreaking laws of motion and gravitation. In his seminal work, Principia Mathematica, Newton recognized the complexity of the three-body problem. He famously lamented to his friend Edmund Halley that the problem gave him sleepless nights and headaches, preferring not to think about it any more than necessary. This problem attracted the attention of many brilliant minds, including French mathematician Henri Poincaré in the late 19th century. Poincaré became involved in the three-body problem during a competition initiated by King Oscar II of Sweden to solve the mysterious motion of three interconnected celestial bodies. His deep understanding of the problem won him the highest award in 1889, and a year later his groundbreaking findings were published in Sur le problème des trois corps et les équations de la dynamique. Small differences in initial conditions give rise to enormous differences in the final phenomenon. Prediction becomes impossible. Henri Poincaré's work was groundbreaking. He discovered that even small changes in the initial conditions of a dynamical system can lead to very different results. This sensitive dependence on initial conditions is a fundamental concept of chaos theory, a field that studies the unpredictable and seemingly random behavior of deterministic systems. It lifted the veil of mystery on what would later be called chaos. In the revolutionary 1960s, chaos theory began its rise to scientific prominence, thanks in large part to a pioneering experiment by meteorologist Edward Lorenz. His task was simple, yet revolutionary, to simulate the behavior of Earth's atmosphere using early computational technology. This attempt not only changed meteorology, but also gave rise to a new understanding of dynamical systems, commonly known today as chaos theory. Edward Lorenz, who had a deep interest in mathematics and meteorology from an early age, found himself in complex theories of weather phenomena after working as a meteorologist in the U.S. Air Force during World War II. After the war, Lorenz enrolled at the Massachusetts Institute of Technology, where he delved into the theoretical underpinnings of atmospheric science. His passion led him to create one of the most avant-garde projects of the era, predicting weather patterns using computational models. At his disposal was the Royal McBee computer, a highly sophisticated machine for its time. In 1960, armed with this technology, Lorenz developed a rudimentary weather model. He reduced the chaotic complexity of Earth's atmosphere to 12 mathematical equations, each of which describes such important variables as temperature, atmospheric pressure, and wind speed at specific time intervals. The model was deterministic. The future state of these variables was calculated based on their current values, with no possibility of random influence. The initial reaction to Lorenz's model was admiring and enthusiastic upon inputting a simple set of numerical data. Royal McBee's computer produced a sequence of numbers, and Lorenz later taught it to draw simple graphs. These sequences, however, revealed something unexpected. Although they came close to repeating patterns, they never truly reproduced them, reflecting the aperiodic and unpredictable nature of real weather. The lack of repeatability, or aperiodicity, in the model results suggested that even small changes in initial conditions could lead to very different results. This phenomenon, which Lorenz would later describe with the metaphorical expression butterfly effect, demonstrated a profound sensitivity to initial conditions, a cornerstone concept of chaos theory. Lorenz's colleagues became enamored of the model. At the Massachusetts Institute of Technology, where minds were always curious and betting on scientific curiosities was commonplace, students and professors placed bets on guessing the model's next results, often finding themselves losing because of the system's unpredictability. This playful participation underscored a critical realization: predicting the weather, or any other system with chaotic elements, is a game of probabilities, not certainties. Winter, 1961. Amid rows of clunky, room-sized computers, 44-year-old meteorologist Edward Lorenz was absorbed in his work at the Massachusetts Institute of Technology, investigating the complex behavior of weather models. Armed with just 12 mathematical equations that represented atmospheric variables, Lorenz embarked on a quest that would fundamentally change our understanding of complex systems. Lorenz's method was to input datasets into his computer, running a cascade of calculations that produced 12 numerical results for each time interval. These numbers were needed to track fluctuations in atmospheric conditions. One fateful day, wanting to dig deeper into the results already obtained, Lorenz stopped the program halfway through, re-entered the data from the previous session, and restarted the simulation from that point. Little did he realize that this simple action would lead to monumental discoveries. Computers in the early 1960s were extremely slow, and it seemed to take eons to process data, so Lorenz decides to go out and get a cup of coffee, giving the machine plenty of time to process the numbers. When he returned, he expected to see familiar patterns on the graph. Instead, he was greeted by a result that was strikingly different from the original, even though the original data and program had remained unchanged. Was it a glitch, or had Lorenz stumbled onto something deeper? This striking moment in Lorenz's biography is often singled out as a turning point, and it is indeed a very important one. It was here that Lorenz noticed and realized something that others had not, something that would later be called the butterfly effect. Physicists like to think as if everything that needs to be done boils down to the phrase, "Here are the initial conditions. What happens next?" Richard Feynman. Back in 1961, Edward Lorenz quickly realized that the problem with the different weather charts was not a faulty computer or a typo. They were remarkably similar in the beginning, but the discrepancy grew with time so that the final results were quite different. James Gleick reproduced a 1961 Lorenz printout in his book Chaos, The Making of a New Science. Here are these two weather graphs originating from the same point. While researching this anomaly, Lorenz discovered the reason for the discrepancy. The computer stored variables with 6 decimal places, but only 3 were stored in the printed results. Lorenz, of course, entered rounded values, reasonably assuming that such precision would suffice. It turned out not to be. This discovery was profound. Lorenz noticed that tiny changes in the raw data could lead to wildly different results, a phenomenon that later became known as the butterfly effect. Then Lorenz tried simplifying the calculations, and then another and another, until he got to 3 equations that described the process of convection, a 2-dimensional model of the atmosphere that heats up at the bottom and cools down at the top. But unfortunately, this did not save the situation. The slightest changes in the data again led to completely different results. Without knowing it himself, Lorenz demonstrated a strong dependence on initial conditions, the basis of chaotic systems. Butterfly effect is a term introduced by Lorenz himself, a reflection of his statement that a butterfly flapping its wings in Brazil can lead to a tornado in Texas. To put it another way, it is the strong dependence of the system on initial conditions, a basic property of dynamic chaos, where even the slightest error in the initial data leads to a completely different result. Despite the fact that the equations in Lorenz's model were only a rough approximation to real weather processes, he realized that we will never be able to achieve a solution to the problem of long-term forecasting. And it's not so much the complexity of calculations, but the unfortunate butterfly effect, as a result of which even small perturbations and inaccuracies over time overlap like a snowball and grow into huge errors. Lorenz did not immediately publish his unusual observation, yet it was rather pessimistic. The triumph of chance and the helplessness of scientists. He decided to delve deeper into the subject and get more extensive data so that he could publish it. Instead of 12 weather equations, he found a shorter version of a chaotic system of 3 non-linear equations for convection, the motion of layers of gas or liquid when heated. They were deceptively simple, but still contained an element of chaos. Lorenz's model of convection has a very illustrative analog that reveals the essence of an aperiodic system. The water wheel. Imagine a small rim similar to a Ferris wheel, but instead of stalls, it has buckets with holes in them. Let's start pouring water from the top with enough pressure to overcome the friction force and make the wheel spin. If the flow remains unchanged, then after a long time, we intuitively expect to find some stability. The wheel will either find the equilibrium position and stop, or it will start spinning in one direction, or its oscillations from side to side will be regularly repeated in time. That is, will be periodic. However, neither of these things will happen. This model is a very vivid example of the fact that chaos and disorder appear not only in huge and complex systems, but also in such primitive constructions. Under the pressure of water filling the containers and flowing out of them through small holes, the wheel behaves in a surprisingly complex way. It slows down its rotation, accelerates it, starts rotating in the other direction, stops, in general, as a self-respecting chaotic system should. The equations looked as follows. To visualize the behavior of the system, Lorenz used a phase portrait rather than the usual time graph. 3 numbers describing the state of the system denoted the coordinates of a point in 3-dimensional space. With each step, a new point appeared on the phase portrait. If the system was coming to complete stability sooner or later, the addition of points sooner or later had to stop completely. If it came to periodic oscillations, the line of points would form a ring. Finally, if there were no regularities in the behavior of the system at all, anything could appear on the phase portrait. The result was completely unexpected. The object that appeared in the portrait was located within certain boundaries without crossing them. Lorenz still hoped to detect some periodicity at large time intervals that could not be noticed at once. But in the end, no set of 3 values ever repeated exactly. However, the pattern became more and more distinct. The lines were not scattered in space. They formed 2 strange, limited swirls, as if the system, despite its complexity, still gravitated toward a specific structure. The image, by an amazing coincidence, resembled a butterfly, as if fixing this symbol for a new science. The science of chaos. The drawing did not stop evolving. No new point coincided with the previous one. The phase portrait could be built endlessly. The transition from one of the wings to the other corresponded to the beginning of the wheel's rotation in the other direction. Such objects, strange attractors, have played a major role in fractal geometry and chaos theory. Butterfly wings have been called the Lorenz Attractor. This is a clear demonstration of the strong dependence on initial conditions. It is worth clarifying that there is nothing random about these systems and equations. If you could still manage to set absolutely identical initial conditions, we would get the same results. The problem is that this is a chaotic system, so even small variations in the conditions at the very beginning escalate to completely dissimilar results. It sounds paradoxical, but this system is both completely deterministic and completely unpredictable. After all, in reality, it is impossible to recreate the initial conditions with absolute precision to an infinite decimal place. Chaos, when the present determines the future, but the approximate present does not approximately determine the future. Edward Lorenz. Lorenz outlined the results of this years-long study in his famous article, Deterministic Non-Periodic Flow, in 1963, which he followed up with several more papers. They undermined the traditional local approach to the study of systems. The hypersensitivity to initial conditions does not allow for the consideration of each element separately, and then their synthesis. How many times have you cursed the weather forecasters when an unexpected downpour turns your weekend plans into indoor movie marathons? In the age of advanced technology, it would seem that predicting the weather with pinpoint accuracy is the easiest thing in the world, right? But weather, despite its impermanence, is still subject to the laws of physics. It used to be thought that our limited computing power was to blame for inaccurate forecasts. However, even with today's arsenal of supercomputers, our ability to predict the weather extends only a few days into the future. Surprisingly, research shows that for forecasts longer than 8 days, it is more reliable to rely on historical averages for a particular date. This is why meteorologists often prepare multiple forecasts, slightly altering initial conditions and development trajectories. But let's delve deeper into the realm of chaos. Chaotic systems are far more common than we can imagine. Take our solar system, for example. Let's take a time travel back about 13.8 billion years, shortly after the theoretically possible Big Bang. At this primitive stage, mere moments had passed, and there was no ordinary matter or energy. The 4 fundamental forces had combined into a single incomprehensible force, and ordinary physical laws had not yet emerged. Instead, the initial evolution of the cosmos was governed by a different set of strict rules. Even the slightest change in any part of the early universe can dramatically alter its future trajectory, regardless of the cause. In fact, the early state of our universe was chaos in the scientific sense of the word. It took about 1 million years for the universe to begin to resemble our current universe, albeit without stars and planets, but with huge clouds of primordial hydrogen. These clouds gradually converged under gravitational forces, forming focal points that would soon become the first stars, massive enough to exert a gravitational influence on each other. even small changes in the position or mass of a protostar can affect not only its own course of evolution, but also that of its nearest neighbors, showing that chaotic principles still dominate the behavior of the universe. Over the next billion years, the first stars ignited and died in explosive events that seeded the universe with heavier elements. New stars emerged from hydrogen clusters, and cosmic dust spiraled into great spirals to form protoplanetary disks. These structures exhibited chaotic patterns and interactions. About 4.5 billion years ago, this process led to the formation of our solar system. Let's return to our main question. Can we predict the future? It seems not, especially for chaotic systems. The further we try to look into the future, the more vague our vision becomes. Eventually, our calculations become mere guesses, lacking substantial accuracy. The same uncertainty characterizes attempts to unravel the past of chaotic systems and decipher initial conditions. It is like peering through a thick fog. The further you strain your eyes, the less you discern. Chaos erects an impenetrable barrier, limiting our understanding of both the history and the future of the system. It should be noted that mastering weather forecasting goes beyond simple algorithms and calculations. It involves managing the complex dance between order and chaos that governs the universe. So the next time you are caught off guard by a sudden downpour, remember that the chaos of nature simply reminds us of its infinite complexity. As Albert Einstein said, "Out of disorder, find simplicity. Out of discord, find harmony. In the midst of difficulty lies opportunity." Some argue that the 20th century will be remembered for three scientific revolutions: the theory of relativity, quantum mechanics, and chaos theory. Lorenz's own merit lies not only in the fact that he encouraged scientists to take a closer look at systems that had previously often been ignored or tried to get rid of. His innate powers of observation allowed him to look at these annoying manifestations of chaos in a different way and see a beautiful idea in them. The butterfly effect is not an accident. It is the essence of the beauty of nature, its uniqueness and diversity. Examples of chaotic systems go far beyond atmospheric vortices. They encompass biological populations, political moods in society, stock market fluctuations, the rhythm of a heartbeat, and even minor changes in a musician's playing. The list could go on ad infinitum. Everywhere we look, we find evidence of deterministic chaos enveloping us. Children grow up, economies develop, and societies undergo transformations. According to these chaotic laws, the entire universe is intertwined with countless connections, and every human being is part of this tangled system. And, most likely, the little butterfly in a far corner of the planet is only what flapped its wing.